Okay, very good morning, one and all. So in the last class, we have started the amplitude shift keying technique. We have initiated the technique and we have gone through the transmitted section of ASK. See, only 15 students joined till now. So what about the remaining students? I think you got information regarding the modified class. Okay, we can go through the topics which we covered in the earlier class, so that meanwhile other students will join. Okay. Next, so let us go through the introduction for ASK. Okay. So, and we discussed that amplitude of the sinusoidal carrier whenever it is switched between two levels 0 and 1, okay, of the input digital signal, then it is called as amplitude shift keying technique. Okay, so the amplitude of this ASK modulated signal is equal to that of carrier. Initially it is equal to that of carrier, but once it is modulated, then you will have amplitude variation in accordance with the input digital signal. So by keeping the frequency and phase as constant. So what is the frequency and phase of ASK signal? It is same as that of carrier component. It is same as that of carrier component. Okay. So what is the frequency of ASK signal? FC. Okay. So what is the phase? It is same as that of carrier. So for carrier component, we assumed the phase as 0. There is no phase deviation. Okay. So here for the ASK signal also the phase remains 0. Okay. Please go through the expression SASK of t is equal to AC cos omega ct when data is equal to 1. Okay. So when data is 0, the magnitude of ASK signal is 0. Because the amplitude of carrier is switched between two levels by keeping the frequency and phase as constant. Okay, and this ASK technique is also called as on-off signaling. So ASK is also called as on-off signaling. So or else you can also call it as on-off key. On-off key. So the acronym for this is OOK. Double O-K. OOK. O-O-K. Okay, so on-off key. Amplitude shift keying technique is also called as on-off keying technique. Okay, so next in the last class we discussed, see here I mentioned ASK technique also called as on-off keying technique. And in this case, because it is binary ASK, only one bit is transmitted per symbol. Only one bit is transmitted per symbol. So that's why T suffix B equals to T suffix S. Because bit duration is equal to symbol duration. Okay, so binary ASK, that's why it is also called as two array ASK. So mean that it has two possibilities of transmitting the signal. Because we are transmitting only one bit per symbol, there are two possibilities. Okay, that you can transmit it as 0 or you can transmit it as 1. Okay. So what are the other names for ASK signal? ASK system, you can also call it as binary ASK because what you are doing here, you are transmitting only one bit per symbol. So that's why bit duration equals to symbol duration. And it is also called as on-off key. Why it is called as on-off key? Because the signal exists only when the data input data is 1 and the signal is off when the data is 0. So you can observe the same thing from this equation. ASK is equal to same AC cos omega ct for the input 1. When the input is 0, it is called as off key. When the input is 0, it is defined as off key. Okay. Now, already we represented ASK signal as AC cos omega ct when the input x of t is 1. Okay. But how can you represent the magnitude of carrier signal as in terms of power dissipation per symbol? So power dissipated per symbol, PS can be defined as AC square by 2R. Okay, because maximum amplitude of carrier by root 2 whole square. That is RMS voltage square divided by R. So it is equals to AC square by 2R. For normalization, you can consider PS is equal to AC square by 2. So that's why we can replace maximum amplitude of carrier as root 2 PS. As root 2ps. Okay, so that's why in the general expression for ASK, we replaced the amplitude of carrier as root 2ps. Okay, so this is the expression for ASK in terms of power dissipation or power dissipated per symbol. Okay, so this exists only when x of t is 1, that is when the input is 1. When the input is 0, this signal don't exist. That's why it is called as on-off keying. So ASK technique is also called as binary ASK or on-off keying technique. Remember these 2 points. And also remember the expressions for ASK. When x of t is equal to 1, it is directly AC cos omega ct. And you can replace AC as root 2ps. You can represent the amplitude of carrier as in terms of power dissipation, power dissipated per symbol. Okay, so let us move to the next slide. In the next slide, you can discuss the representation of ASK signal in terms of 1-bit energy carrier. So with we know that energy can be represented as the product of power and time. Okay, so power dissipated per symbol and symbol duration is the symbol energy. So now our intention is to represent this power dissipation in terms of energy. Okay, so because we are showing interest to calculate the Euclidean distance. Okay, so ASK signal can be represented as root ps into ts. Our intention is to represent the equation in terms of energy. Okay, that is root es into root 2 by ts cos omega ct by rearranging such a way that dividing and multiplying with respect to root ts, you can get the expression as root ps ts into root 2 by ts into cos omega ct. Okay, so now here you can replace phi1 of t as root 2 by ts into cos omega ct, where phi1 of t is the 1-bit energy carrier, where phi1 of t is the 1-bit energy carrier. Okay, so which you can represent as root 2 by ts into cos omega ct. Okay, so please always remember that here, because in the case of binary ASK, only 1 bit is transmitted per symbol. Only 1 bit is transmitted per symbol. In binary ASK, only 1 bit is transmitted per symbol. Okay, that's why we will have only 1-bit energy carrier. We'll have only 1-bit energy carrier. Okay, we will get 2 bits energy carriers like phi1 of t and phi2 of t. Okay, 2 energy carriers will be there. When you will have phi1 of t and phi2 of t if we transmit 2 data bits per symbol. Okay, for example, if we transmit 3 data bits per symbol, then we'll have 3 energy carriers. Okay, so like that, whenever you have the number of, based on the number of bits transmitted per symbol, you will have that many number of energy carriers. Okay, but here we'll have only 1-bit energy carrier, that is phi1 of t. But in M-array transmission technique, you will have n number of energy carriers, n number of 1-bit energy carriers. Okay, so how can you replace the ASK signal now? Root es into phi1 of t, root es into phi1 of t, where phi1 of t is root 2 by ts cos omega ct. Okay, this is when input data x of t is 1. But when the input data x of t is 0, there is no component present. So the magnitude is 0. The magnitude is 0. Okay, so here always remember that symbol energy is equal to the product of power dissipated per symbol and symbol duration. Okay, and for the BPSK, bit duration is equal to symbol duration. Bit duration equals to symbol duration. Okay, this is how we can represent the ASK signal in terms of amplitude of carrier, in terms of power dissipation, and in terms of symbol energy. Okay. So our intention is to calculate the Euclidean distance. This you can calculate by taking the 1-bit energy carrier, so representation of 1-bit carrier energy in signal space. 1-bit energy carrier in signal space. This diagram is also called as geometrical representation or signal space representation. Okay, for example, if you have more number of energy carriers, for example, if it is 2, those 2 are perpendicular to each other. If it is 3, the 3 are perpendicular to each other. Like that, you will get XYZ axis. And in such a way that, for example, there are n number of bits transmitted per symbol, then all the energy carriers are perpendicular to each other. Okay. So what is the Euclidean distance? Euclidean distance is a difference between the magnitude of 1-bit energy carrier, for data 1 and 1-bit energy carrier for data 0. Okay, so magnitude of 1-bit energy carrier for data 1 is how much? It is a root ES or root PS into TS. And the magnitude of 1-bit carrier energy for data 0 is 0. Okay, so you will get it as root PS into TS. So what is the conclusion here? As and when the Euclidean distance increases, the isolation between the 2 points will increase. Once the isolation increases at the receiver, you easily distinguish the levels 0 and 1. Thereby, the probability of error will reduce. So what is the conclusion here? The probability of error will reduce when the Euclidean distance is more. But here Euclidean distance is very less and it is equal to just root ES, that's all, where ES is equal to root PS into TS. In this case, you can replace symbol duration as bit duration because we are transmitting only 1 bit per symbol. Okay. Let us move to the next slide so that you can generate binary ASK signal. How can we generate binary ASK signal? Before going to the generation technique, please one of the student respond and tell me the general expression for ASK signal in terms of amplitude of carrier, in terms of power dissipated per symbol, and in terms of symbol energy. So any one of the student, please voluntarily come up and tell me the expressions for ASK signal. Any one of the student, please. Any one of the student kindly tell me the expression for ASK signal. K0, K0, K2, K2, K5.
Ma'am.
Can you tell me the expression for ASK signal in terms of amplitude of carrier and in terms of power dissipated per symbol and also in terms of energy, symbol energy?
Yes, ma'am.
Please tell.
AC into cos omega CT.
Okay. Continue. Please continue.
Yes, ma'am. In terms of power dissipated, it is root over 2 PS into cos omega CT.
Yes. Tell me the same expression in terms of symbol energy.
Symbol and it is root over ES.
Root ES into phi 1 of T.
Phi 1 of T.
What is phi 1 of T? 1 bit energy carrier. Can you tell me the expression for phi 1 of T?
Yes, ma'am. It is root over 2 by TS into cos omega CT.
Yes, root over 2 by Ts into cos omega Ct. This is all for the input 1, when the input data bit is 1. What is the magnitude of ASK signal when the input data is 0?
0, ma'am.
Yes, it is completely, there is no magnitude at all. Okay, okay, thank you, Ma, thank you. And wait, one more thing. What is the Euclidean distance for ASK signal?
Yeah.
What is the Euclidean distance for ASK signal?
Whole root PS into TS.
Okay. What is the bandwidth of ASK signal?
And
We already studied in the last class. Okay, once again I will revise. Thank you, Ma. Thank you.
minus FB to plus FB.
Yes, it is 2 TB to FB. Okay, bandwidth is 2 FB. Okay, thank you, Ma. You can mute. Thank you. Now, let us go to the generation of binary ASK signal. Already we have seen this slide in the last class. Okay, so how can you generate an ASK signal? This is very simple to generate. Just it is the product of unipolar energid and sinusoidal carrier. Okay, so we have two inputs to the modulator. What are the two inputs? One is unipolar energid and other is the carrier. Whenever unipolar energid is multiplied with sinusoidal carrier, we can generate ASK signal. Okay, and now any other student, can you tell me what is the frequency of binary ASK? It is same as that of carrier, because for the carrier the frequency is FC, and for the binary ASK signal you won't have any kind of frequency variations. The frequency and phase of ASK signal is same as that of carrier, but we'll have only amplitude variations. Okay, how the amplitude will differ? Based on the input, that is unipolar energid. Based on unipolar energid, we can generate binary ASK signal whose magnitude varies with respect to the unipolar energid magnitude. Okay, and the frequency and phase of binary ASK is same as that of carrier. Okay, so it is applied to the band pass filter to extract the band limited ASK signal, so that our ASK signal magnitude frequency changes from FC minus FB to FC plus FB. Okay, so what is the bandwidth of ASK signal then? 2 FB. Okay, what is the bandwidth of ASK? 2 FB. So what is the simple procedure to generate ASK signal? Unipolar energid is multiplied with sinusoidal carrier to generate ASK signal. Please, all of the students, remember this block diagram, and the block like the generation technique for the PSK, that is phase shift keying, is almost all similar to the block diagram shown here. So the principle behind generation of ASK signal and PSK signal is same. So instead of unipolar energid, we will make use of bipolar energid. Okay, a bipolar energid is multiplied by sinusoidal carrier to generate binary phase shift keying or PSK signal, that is phase shift keying modulated signal. Instead of bipolar, if you take unipolar energid, we can generate ASK signal. Okay, we can go to the next slide so that you can see it clear. So please observe the waveforms. Please observe the first figure, that is unipolar energid. Okay, so we consider the input sequence as 1 0 1 1 0 1 0 1 1 1. Okay, so here unipolar mean that the signal flow is only in the positive direction. Signal flow is only in the positive direction, and for the magnitude 1, whenever the input data is 1, we'll have high level, and for the input data bit 0, we'll have 0 level. Don't think that here we don't get negative level. Here we don't get negative level. But in the case of bipolar energy, which we'll take for phase shift keying, we'll have negative level because signal flow is in the both the directions. Okay, for the 0 data bit, magnitude is at low level. For the 1 data bit, magnitude is at high level. Now, what is the second input? Sinusoidal carrier is required to modulate the signal. So for the sinusoidal carrier, the frequency is greater than that of the frequency of the input signal. Okay, so two cycles are required. 2 cycles are required to complete a 1 bit interval. Okay, so frequency of carrier, we can say it is double to that of frequency of the input signal. Okay. Now, if you observe the ASK signal, for the data bit 1, same carrier will be represented at the output. For the data bit 0, we have 0 magnitude. So that's why 0 magnitude is represented. And similarly, for the next two data bits 1, 1, we'll have same magnitude as carrier. Okay, whenever we get a 0 data bit, the magnitude of ASK signal is 0. And whenever we have data bit 1, the magnitude is same as that of carrier. Okay, for the data bit 0, magnitude is 0. For the data bit 1, magnitude of ASK is same as that of carrier. Okay, so this is all about the ASK waveforms. You can see the spectral response in the next slide. Please observe the spectral response. If you observe the spectral response here of input signal, so what is the time interval of a particular bit? It is T suffix B. Please observe, you have left two columns here. First column represents the time representation, okay, or the signal variation with respect to time. And the second column figures represent the spectral response, of the corresponding waveforms shown in the left column. See, please observe the first figure in the left column. It is the digital signal. It is the digital signal whose series is 1010. 1010. So, and also observe that for the 0 level, the magnitude of digital signal is not 0. We have some magnitude. Okay, that magnitude we will get at the output of ASK for data bit 0. Okay, now this is 1010 series with a bit duration of T suffix B. Okay, next please, second figure represents the carrier frequency before modulation. So before modulation, carrier signal is AC cos omega CT. Okay, so same free component we represented here. So the frequency of carrier is higher than that of the input digital signal. Okay, so next third figure in the first column represents the ASK signal. That is nothing but the carrier frequency FC plus or minus FB after ASK modulation. Okay, so for the data bit 1, you can observe the same carrier signal is reproduced. For the data bit 0, instead of 0 magnitude, you will get some magnitude, because here in the input digital signal, for the 0 level, the magnitude is not 0. We have some magnitude. The same magnitude is reproduced at the output, that is at the modulation. After ASK modulation, you will get the same magnitude for data bit 0. So like that, you will get ASK modulated signal. Please accordingly observe the spectral response. What is the bit interval? T suffix B. Okay, so the reciprocal of that will be the bit frequency. You can observe the same spectral response of the input digital signal versus frequency. So because it is a band limited signal, and that bandwidth is plus or minus FB. So that's why within that duration you will have maximum magnitude, and beyond that plus or minus FB, you don't have any signal component. Okay, so what is the bandwidth of digital signal? Plus or minus FB. Okay, the same thing is reproduced here. If you take only the positive real frequency component, the frequency is f suffix b. Okay, next please observe the carrier. We already know that. Please observe the second figure in the second column. So it is the spectral response of carrier frequency. It is the spectral response of carrier frequency. So carrier frequency, carrier is represented as AC cos omega ct. Okay, so you can represent cos as e power j omega ct plus e power minus j omega ct divided by 2. Okay, we already know, we studied in analog communication that the Fourier transform of cos omega ct consists of two impulses located at plus or minus fc. Because Fourier transform of e power j omega ct plus e power minus j omega ct divided by 2, you will get pi 2 pi del of f minus fc plus 2 pi del of f minus fc. So two impulses located at plus or minus fc. That is the spectral response of carrier component. And you can observe, here we represented fc as greater than fb from center location, that is from 0. Fb is nearer to 0 and fc is somewhat greater than that of fb. That's why while representing the carrier, please represent fc far greater than fb. Okay, so these two are the inputs, and in time you are applying via the via the multiplier. Okay, so in frequency response you need to apply it to the convolution. Okay, so in time domain, if you have multiplication, in frequency, the multiplication in time domain you can replace with convolution in frequency domain. So convolution of these two signals gives you 3 spectral responses. Okay, 3 spectral responses on the positive real frequencies as well as on the negative real frequencies. So in general, negative frequencies are not considerable or not preferable for real-time applications. Okay, so only the positive real frequencies are considered, and the signal exists only from fc minus fb to fc plus fb. fc minus fb to fc plus fb. Okay, so what is the bandwidth? Bandwidth is defined as the upper cutoff frequency minus lower cutoff frequency. So what is the upper cutoff frequency? fc plus fb, because at fc you will have carrier frequency, and our distribution range from minus fb to plus fb, so that the upper cutoff will be fc plus fb and lower cutoff will be fc minus fb. Okay, so the bandwidth of ASK signal is equal to in general, the definition is the difference between the upper cutoff frequency and lower cutoff frequency. So you can represent fc plus fb minus of fc minus fb. So it will be 2fb. So what is the bandwidth of ASK signal? 2fb. In terms of bandwidth, our ASK signal provides the best response. Okay, in terms of bandwidth, the ASK system provides the best response. It's a bandwidth efficient technique because its bandwidth is only 2fb, where fb is far less than fc. Okay, so practical in the real-time applications, the practical bandwidth of ASK signal is 3fb. What is the practical bandwidth of ASK signal? 3fb, but the general bandwidth is 2fb. Okay, now, so until now we studied the generation technique, spectral response, that is the calculation of bandwidth, and then what we did, we have gone through the Euclidean distance evaluation and the general expression for ASK. Now let us go to the detection techniques of ASK. Okay, so in general we have two detection techniques. One is coherent detection and second one is non-coherent detection. For any technique, for any digital communication technique, we have two kinds of detection. That may be for ASK or phase shift keying or frequency shift keying. We have two kinds of detection techniques. One is coherent detection and second one is called as non-coherent detection. Coherent detection is also called as synchronous demodulation. coherent detection is also called as synchronous demodulation. Okay, and here in the case of coherent detection, synchronous carrier is used. In the case of coherent detection, synchronous carrier is used. Okay, so what is meant by synchronous carrier? So it should be in phase lock with the carrier used at the transmitter section. Okay, so what is non-coherent detection? It is also called as asynchronous carrier. Here we don't make use of synchronous carrier. Okay, now so we need to study two different kinds of detection techniques for the modulation, for the ASK modulation technique. Now let us go through the coherent detection. Okay, so this is the coherent detection of binary ASK signal. This is generally used at the receiver section. Okay, so we know that what is the input to the receiver section? Modulated signal. Okay, so the modulated signal, it's a noisy modulated signal. So what is the input to the receiver? Noisy modulated signal. But here we are using ASK technique, that is amplitude shift keying technique. Okay, so what can be the input to the receiver? Noisy amplitude shift keying modulated signal acts as input to the receiver. Okay, so coming to the coherent detection, it consists of three sections. See, always remember, in the coherent detection, we need to make use of synchronous carrier. Please remember, in the coherent detection, for any kind of modulation, we should make use of synchronous carrier as one of the input to the multiplier. Okay. Now, so what are the three sections in coherent detection of ASK? Multiplier, low pass filter, and decision device. Multiplier, low pass filter, and decision device. These are the three elements used to reconstruct the input signal or digital signal using ASK technique. Now what is the input to the receiver? Noisy band limited ASK signal acts as input to the receiver section. Well, now this is applied to the multiplier. What is the other input to the multiplier? Synchronous carrier. What is the other input to the multiplier? Synchronous carrier. So synchronous carrier along with the noisy band limited ASK signal, or both are fed to the multiplier. Okay, so what this multiplier will do? Multiplier takes the product of noisy ASK signal with synchronous carrier. Now what is synchronization actually? So we are telling that synchronous carrier is a one which should be in phase lock with the transmitter carrier. Okay, so what is our synchronous carrier? Synchronous carrier is also called as coherent carrier. Where the two, detection includes a synchronous carrier which is also called as coherent carrier, that is in phase lock with that of the transmitter carrier. At the transmitter section, we will make use of a carrier component. So the same frequency and same phase and the same timing at the same switching instance you should consider. So that is nothing but phase lock. So our synchronous carrier should be in phase lock to that of transmitter carrier. Okay, so what is meant by phase lock? We are telling that a receiver carrier should be in phase lock with the transmitter carrier. What is meant by phase lock? In general, in order to satisfy the phase lock, or in order to provide a synchronization, phase lock should be, one is synchronization for both frequency and phase. Second one is timing synchronization is also necessary. So what is the first one? That is frequency and phase synchronization. Okay, frequency or phase synchronization. So it means that here we have the frequency and phase of the receiver carrier is same as that of the frequency and phase of the transmitter carrier. Okay, that is the first synchronization, that is frequency or phase synchronization. Second one is timing synchronization. So it means that the synchronization provided by the receiver, that is the switching instance, or you can say the sampling intervals. So the switching instance of the receiver should match with that of the transmitter section. So that is generally called as timing synchronization. So this coherent carrier used at the receiver. So coherent carrier is also called as synchronous carrier. This should undergo two kinds of synchronization. One is frequency and phase. Second one is timing synchronization. Okay, frequency or phase synchronization. Second one is timings should also match. Okay, so switching instance of the receiver should match with the switching instance of transmitter section. Okay, this is the coherent detection of binary ASK. Now let us go through the mathematical analysis. Okay, so while calculation of mathematical analysis, what is the input to the ASK, like this receiver section? Band limited ASK signal. What is the general expression for ASK? What is the general expression for ASK? Tell me in terms of amplitude of carrier. Simply AC cos omega CT when data is 1 and when the input x of t is 0, our ASK signal is also 0. Okay, now that is applied to the synchronous carrier. So that is applied to the multiplier whose other input is a synchronous carrier. Whose other input is synchronous carrier. So both are applied to the multiplier. Both are applied to the multiplier. And the multiplier output will be fed to the low pass filter. We know that low pass filter smoothens the output of multiplier by eliminating the higher frequencies. Low pass filter smoothens the multiplier output by eliminating the higher frequency components. Okay, and the output of low pass filter is compared with the reference voltage. What is this reference voltage? This is a predefined threshold value. This is the predefined threshold value. Okay, applied as one of the input to the decision device. This decision device compares the output of the low pass filter with the predefined reference voltage or threshold voltage. Okay, so whenever the low pass, you can also call this decision device utilization as a comparator. Okay, you can also call this section as a comparator. Here this section compares the low pass filter output with the reference voltage and provides a decision. Okay, and provides the decision as either 1 or 0, either 1 or 0. The decision is 1. The decision is 1 when the low pass filter output is greater than the reference voltage, is greater than the reference voltage. The magnitude is less than, if for example, if the low pass filter magnitude is less than the threshold, that is V reference, then comparator provides a decision as 0. So based on the magnitude of low pass filter, it generates as 1 or 0 if low pass filter output is greater than V reference, and 0 when low pass filter output is less than V reference. Okay, let us go to the next slide so that you can see the mathematical analysis. Now, let us go through the mathematical analysis. So what is the synchronous carrier? Let us assume the synchronous carrier as C suffix S. Okay, this synchronous carrier should, what are the two types of synchronizations that it should to undergo phase lock? One is frequency or phase synchronization, and second one is timing synchronization. Okay, so timing synchronization is provided, okay, by the corresponding sampling techniques. So before generation of a digital signal itself, proper switching instances are used. And how the frequency or phase synchronization can be possible? The frequency and phase, that is frequency and phase, should match to that of transmitter carrier. So here the frequency of receiver carrier is FC. Frequency of receiver carrier is FC. Okay, and phase of transmitter carrier is 0. So that's why here we did not take omega Ct plus 5. 5 we considered as 0. And the magnitude of carrier we considered as 1 ohm, 1 volt. Okay, let us consider, for simplification, let us consider amplitude of carrier, maximum amplitude of carrier as 1 volt. Okay, let us consider it as 1 volt. Now, what is the other input to the multiplier? So, multiplier has two inputs. One is the synchronous carrier, and the main input is noisy ASK signal. Okay, let us consider first the evaluation using the ASK signal. Okay, so what is the general form of ASK signal, or when the ASK signal will exist? When x of t is 1, ASK signal will exist. Okay, that as AC cos omega ct. AC cos omega ct. Okay, when x of t is 0, when x of t is 0, ASK signal don't exist. ASK signal do not exist when x of t is 0, and when input data x of t is 1, then it exists and it is equal to AC cos omega ct. Now what is the multiplier output? So multiplier output will also exist only for the data 1 and it won't exist for data 0, because multiplier output is a product of ASK signal and carrier. So 0 multiplied by any factor will be 0 only. So multiplier output is 0 for data 0, and for data 1, please observe, take the product of ASK and signal and carrier. We assumed the synchronous carrier as cos omega ct with phase variation as 0 and amplitude of carrier as 1 volt. Okay. Now it is the product of ASK signal and carrier, that is AC cos omega ct is ASK signal multiplied by cos omega ct, that is synchronous carrier. So then you will get AC cos square omega ct. You will get AC cos square omega ct. Okay, and it is cos square, you can represent it as using trigonometric expressions. You can represent cos square omega ct as 1 plus cos 2 omega ct divided by 2. That's why we took AC by 2. AC by 2 multiplied by 1 plus cos cos 2 omega ct. Now this is you split the expression because it is 1 plus cos 2 omega ct divided by 2. So you will get AC by 2 plus AC by 2 into cos 2 omega ct. This is for data bit 1. And for data 0, the multiplier output is 0. Now this multiplier output is fed to the low pass filter. Fed to the low pass filter. Now can any one of you tell me what is the low pass filter output for data 1? Can any one of you tell me what is the low pass filter output? Because the multiplier output is fed to the low pass filter. Okay, multiplier output is AC by 2 plus AC by 2 into cos 2 omega ct for data bit 1. For data 0, it is 0. Now this output is fed to the low pass filter. So can any one of you tell me what is the output of low pass filter?
AC by 2.
Yes, only AC by 2, because 2 omega ct gets cancelled, because 2 omega ct do not, our low pass filter do not allow a high frequency component. Omega c is a higher value, so 2 omega c will be twice that of the magnitude. So our low pass filter do not allow the 2 omega c component. So that's why the output is only AC by 2. Low pass filter output will be AC by 2 for data 1, and for data 0 it is 0. Now the low pass filter, what is the third section? Low pass filter output is fed to the comparator. So you can also call it as a decision device. Okay, so now this decision device, what it will do? It will compare the low pass filter output with reference voltage. Low pass filter output with the reference voltage. So the decision device output is 1 when the low pass filter output, that is AC by 2, is greater than V reference. V reference is a predefined threshold value and that is given by the designer itself. Okay, and it is 0 when low pass filter output, that is AC by 2, is less than or equal to V reference. Okay, this is all about the coherent detection of binary ASK signal. Now please tell me, here we consider the synchronous carrier as AC cos omega ct. Sorry, assuming AC as 1. For example, instead of assuming AC as 1, if you take AC cos omega ct, for example, if AC not equals to 1, then what is the low pass filter output? Instead of AC by 2, you will get it as, actually here we assumed the carrier as cos omega ct considering AC as 1 volt. If AC is not equal to 1 volt, for example, take it as AC cos omega ct, then what is the multiplier output? Any one of you? J5, J5.
Yes, ma'am.
Okay, so here we assumed the synchronous carrier as cos omega ct. We assumed AC as 1 volt. Okay. For example, if you take it as AC and tell me the multiplier output.
AC
cos square omega ct.
అమ్మా చెప్పండి ఒకసారి, ప్లీజ్ టెల్ మీ.
Cos square omega ct.
Cos square omega ct, instead of cos omega ct, if you take AC cos omega ct as synchronous carrier, then output will be, multiplier output will be CS of t ni AC cos omega ct. Please consider CS of t as AC cos omega ct.
AC square
AC square
cos omega c square t.
AC square by 2 plus AC square by 2 into cos 2 omega ct. Now, okay, that is applied to the low pass filter. What is the low pass filter output at that time? What is the low pass filter output when the carrier is AC cos omega ct?
AC square by 2.
Yes, it is only AC square by 2 because AC cos omega ct into AC cos omega ct. So it is AC square cos square omega ct. So it will be AC square by 2 plus AC square by 2 into cos 2 omega ct. If it is allowed to the low pass filter do not allow 2 omega ct component. So instead of AC by 2, you will get the low pass filter output as AC square by 2. Okay. If you consider the amplitude of synchronous carrier as AC cos omega ct, then you will get low pass filter output as AC by 2. If you take AC as 1 volt, okay, you will get AC by 2. If you don't take it as 1 volt, you will get AC square by 2. That's all. You will get square. So anyhow, we assumed AC as 1 volt. So that's why low pass filter output is AC by 2 only. Okay, ma, thank you. So that's why decision device output is 1 when AC by 2 is greater than V reference, and it is 0 when AC by 2 is less than or equal to V reference. Now, so what is a coherent detector? What this coherent detector will do? It estimates the output signal. It estimates the output signal with less probability of error, because here we are using a synchronous carrier. Because we are using synchronous carrier, it estimates the output signal with less probability of error. But the implementation, the receiver implementation is difficult compared to non-coherent detection. Compared to non-coherent detection, coherent detection implementation is somewhat difficult. Okay, but it generates less probability of error because we are using synchronous carrier. Okay. Now let us go through the non-coherent detection. So this is the, please observe the figure. Please observe the figure. This is the non-coherent detection of binary ASK signal. So what is the other name for non-coherent detection? Asynchronous detection. Why it is called as asynchronous detection? Because here we don't make use of synchronous carrier. Here we don't make use of synchronous carrier. So here you can observe there is no input like carrier, synchronous carrier in the circuit. But in the case of earlier coherent detection, we used synchronous carrier. We used synchronous carrier. If synchronous carrier is used, we used a multiplier to multiply ASK signal with carrier. But here, can you observe any synchronous carrier anywhere at the receiver section? No. It don't make use of synchronous carrier. So that's why it leads to increase in the probability of error. So this kind of circuit is preferable only for the laboratory applications, and coherent detection is used in real-time applications. And the circuit is simple over coherent detection. Okay, please observe the circuit. How many sections are there? It consists of 3 sections. See, last section, decision device, is common for any kind of like detection technique, that may be coherent or non-coherent, but you need decision device, okay, to convert into digital. So decision device is used to convert the signal into digital signal consisting of only 2 levels, because decision device generates only the output at 2 levels. If it is greater than threshold, it will be 1. If it is less than threshold, the data output is 0. Okay, so that's why this type of non-coherent detection techniques are used in laboratory applications, where it leads to the large probability of error. Okay, and what about the BASK signal? It is fed to the band pass filter. It has cutoff from FC minus FB to FC plus FB. So what is the cutoff of band pass filter here? In order to generate band limited ASK signal, we are using in the front end we are using band pass filter. That is applied to the envelope detector. That is applied to the envelope detector. So I think you know regarding the envelope detector. Envelope detector is the amplitude demodulator. Okay, so it uses a diode followed by low pass filter. So rectifier section consists of a diode in the forward path. Okay, so rectifier, we know that it converts alternating current into DC component. Okay, direct current component. Pulsating DC it will generate. Okay, what this envelope detector consists of? Envelope detector consists of a rectifier followed by low pass filter. Rectifier followed by low pass filter. What this rectifier will do? Rectifier converts alternating signal into pulsating DC. Alternating signal into pulsating DC. This is smoothened by the low pass filter. So envelope detector consists of rectifier section followed by low pass filter. Okay, so rectifier converts alternating component into pulsating DC, and that pulsating DC will be smoothened by the low pass filter. Okay, so low pass filter output is once again compared with the threshold value. Okay, so if the low pass filter output is greater than that threshold, we'll get the output as 1. If it is less than or equal to threshold, the output is 0. Okay, this is all about the difference between the coherent and non-coherent detection of binary ASK signal. Okay, now we can go to the next slide. Okay. So in this slide, you can see the advantages and disadvantages of binary ASK signal. See, observe the advantages. Please observe the advantages. Here the circuit is simple and inexpensive. Okay, and the transmitter section remains idle during the transmission of ASK signal for input 0. Okay, so transmitter section remains idle during the transmission of ASK signal for input 0. For the input 1 only, ASK signal magnitude is same as that of carrier. For input 0, ASK signal magnitude is also 0. So we don't transmit any component at that time. So that's why it provides or it preserves the power during the transmission of 0. So it's power efficient. So it conserves the utilization of power, or it preserves the power, and its bandwidth is very high. Okay, So bandwidth is 2 FB only, not very high. It has high efficiency. It has high bandwidth efficiency. Okay, anyhow, time up. Actually, I have one more session for C section now. So tomorrow we can continue the advantages and disadvantages of ASK signal. So till now we completed the generation of ASK and two types of detection also we studied, that is coherent and non-coherent detection. So in the next class we can continue with binary PSK technique. So after completion of the advantages and disadvantages of ASK, we can go through the phase shift keying technique. Okay, please wait for 1 minute. I will take the attendance. And one more thing is, please join by 9:30 itself whenever we have first hour session. Okay. Okay, you can leave. I took the attendance, you can leave now.